Today it's my pleasure to introduce my colleague Lorenzo Lovisari to give us a talk. And Lorenzo is from Italy. He previously went to University of Bologna, and then he moved to University of Innsbruck, where he got his PhD in 2010. And then after that, he moved to University of Bonn, and as his first postdoc, working with Thomas Ripprich. And his expertise is on groups of galaxies and the enrichment of the hot gas in the groups of galaxies and cluster of galaxies. Thank you.
Thank you, Jojo. So for the people that do not know me, for a while I was known as the famous Lorenzo, and fortunately not for my scientific results, but because I was at the conference, the hiking conference in the Austrian Alps. And while we were at the 3,000 meters, I fell down and I hit my foot. I couldn't walk anymore. And I've been rescued by an helicopter. And the picture they take my colleagues here, and this poster was in many walls in Europe, and I think also Craig Sardin used this picture to show that science can be interesting around the world. Anyway, today I'm not going to speak about that. I'm going to speak about the galaxy groups that are also interesting. I apologize with the people that were at the postdoc symposium a few weeks ago. Most of the slides I already showed there. So the first question one would like to answer is what is the difference between galaxy groups and galaxy clusters? There is no trivial answer to that question because there are not strict boundaries between these two systems. So I try to give some number here, but I'm pretty sure that some of the people in the audience would disagree with some of them. But this is my talk and they have to live with them today. So one thing we could agree is that for the typical galaxy groups, they have a very few bright galaxies. And that made very hard in the past their optical detection with a good accuracy. And that prevented for a long time a careful studies of these systems. Due to their faint emission, also the X-ray detection was pretty hard. And even when you can detect them and you want to measure the radial properties, that is quite challenging because you are very soon dominated by the background. So the obvious question is why do we care about that, the galaxy groups, if they are so hard to detect and to analyze them? The reason is that the currently accepted scenario of structural formation, the most massive structures form through episodic merger of small mass units and the continuous accretion of the field galaxies. And due to that, the halo mass function of virialized systems, which represents the number density of galaxy groups and clusters above a threshold mass m, is quite steep. And that makes galaxy groups a much more common environment than galaxy clusters. And at the low redshift, they actually contain the largest fraction of the baryons. In practice, they are the building blocks of the future galaxy clusters. So to study the properties of the galaxy groups may give us some information about the formation and evolution of the most massive systems. Moreover, their low mass, since they are very low, they have a very low masses, the non-gravitational processes might dominate over the gravity. And here you have a plot from Giodini and collaborators where they compare the binding energy of the systems, both groups and clusters, versus the input energy of the central galaxy that they estimated using the radioluminosity of the central galaxy. And while for galaxy cluster, the binding energy is 2-3 orders of magnitudes higher than the input energy from the central galaxy, at the galaxy group scale, the two energies are almost comparable. And that means that it might happen that the central galaxies eject enough energy to unbind some of the gas. The same baryon physics is at work at the cluster scale, and even if not dominant, it might be still significant, and it can change the properties of the galaxy clusters. So if we want to further improve the cosmological constraint on using galaxy cluster, we need to take into account the non-gravitational processes also at the cluster scale. And that can be done easily at the group scale, where their effect is larger due to their shallower potential wear. There is an extra reason to focus on the galaxy groups, and is eROSITA. eROSITA is a German mission that will be launched in March 2017, and after 3 months of travel, we reach the L2 point, and it will start to scan the sky for 4 years before moving to a pointing phase. And during these 4 years, it will increase the detection sensitivity with respect to ROSITA by 1 order of magnitude, as you can see in these 2 plots, where the predicted detection sensitivity for eROSITA is compared with other existing survey from ROSITA in green, XMM in blue, and Chandra in purple. You may probably recognize some of them. But what is the link between eROSITA and the galaxy groups? So eROSITA is promising to detect more than 100,000 galaxy groups and galaxy clusters, increasing our statistical power by 1 or 2 orders of magnitude, because the largest X-ray catalog that we have nowadays contain less of 2,000 objects. And the best studies on the cosmological parameters with the X-ray samples have been performed with less of 100 objects. So it will be a big step, but most of these objects will be actually in the low mass regime. So as you can see, more than a half will have a mass lower than 10 to 14, that accordingly to the tables that I showed at the beginning will translate in roughly 2-3 keV temperatures, so they are actually galaxy groups. For most of these objects, eROSITA won't be able to detect many photons, so we won't be able to derive the density and temperature profiles required to apply the hydrostatic equilibrium equation. So we will rely almost completely on the scaling relations. So how well we will be able to convert some observables like the luminosity and the temperature into the total masses that will be used to build the halo mass function and derive the cosmological parameters. We would prefer to use the temperature instead of the luminosity, because the mass temperature relation is less scattered than the luminosity mass relation. So we tried with one of the PhD students working with me and Thomas in Bonn to simulate, to estimate for how many objects we will be able to determine the temperature with an accuracy better than 10%. And we performed the simulation for different redshift and for different masses. And we didn't simulate this region of the plot, because for these objects we have already plenty of data from Chandra, XMM, and Suzaku, and we won't be able to do better with eROSITA. And the result is that for only 4 objects with a redshift below, let's say, 0.1, 0.15, we can measure with the eROSITA data only a temperature with an accuracy better than 10%. But to do that, we need to know the redshift. And so we need some optical follow-up to have some spectroscopic or at least photometric information, which probably will not be available for many years, because it will require a lot of time to follow up 100,000 objects. If we require eROSITA to detect also the redshift, then the number of objects for which we can determine the temperature with a relatively good accuracy decrease quite a lot, and we estimated that it will be for roughly 200-300 objects only. So we really need a certain point if we want to use the temperature to have some X-ray follow-up with other instruments, and we hope that Chandra XMM will still be in orbit. Of course, if we can do some follow-up with a subsample of these objects, we may use also other max proxies like the YX or M gas that are less scattered than these 2 relations. At the group scale, the scaling relations are even more uncertain than the one at the galaxy cluster scale. We have several works showing that there is a steepening of the scaling relation when you move in the low mass regime. But other results show that there is actually a quite good agreement between the properties of the galaxy groups and the galaxy cluster. So it's not clear yet if we can treat the galaxy groups as galaxy clusters, so if we can use a single power law relation when converting the luminosity or other mass process to the masses. And moreover, none of this work about the galaxy groups took into account the selection bias effects, something that was indeed done for more massive systems. And the effect of the selection biases is showed in this nice plot by Mans and collaborators, where on the left panel you can see the true luminosity and masses for the simulated objects following a power law relation with an intrinsic, a log normal intrinsic scatter. And on the right panel you have a simple survey where you require a constant threshold luminosity for detection. Now, even if you could measure perfectly the luminosity and masses for the detected objects, a naive fit of the data will never recover the underlying power law relation. You will find something probably flatter here. And if you use the observed relation to convert the luminosity into the total masses, then you will build a biased halo mass function, you derive a biased cosmological parameters. So this effect need to be taken into account if you want to use the scaling relation to do cosmology. So how do we select our sample? So we basically started from two input catalogs, Norras and Reflex, obtained with the ROSAT data, that were the same catalog used to build the iFlux sample, which is a sample, a flux-limited sample that contains mainly massive systems, and they are the brightest objects in the universe. And we lower down the iFlux limit until a reasonable amount of objects were included in the sample to allow us to derive the scaling properties. We also applied two redshift cuts. The lowest one is to ensure that a relatively large fraction of the group volume fall within the XMM field of view, and the larger value is to prevent actually galaxy cluster to be sampled in our selection, so that we have a sample of only galaxy groups. This is the distribution of the sky of the galaxy groups showed in red and compared with the distribution of the sky of the high flux sample. It's not really important, the distribution here, but it's important to note that if we combine the two samples, we build a master sample that is spanning over 3 orders of magnitude in luminosity and 2 orders of magnitude in masses. And this is very important when studying the scaling relation because it helps to break the degeneracy between the slope and the normalization. I don't have time to go into the detail of the selection bias correction, but I will give you some the basic steps to allow you to understand the methods that we used to correct for this bias. So we basically started from a halo mass function. We used as a reference the Tinker mass function, and from the Tinker mass function we have the masses and redshift for all the simulated objects. Then we assign to every object a luminosity through an input LM relation. This input LM relation is the relation corrected for selection biases, the relation that we are searching for. And the slope and normalization for the input LM relation were varied in a grid spanning a larger range of values. After applying this, after assigning the luminosity, we have the redshift, so we have also the flux, and we can apply to the simulated sample the same selection criteria as in our observed sample, and we can fit the data with the same observations, with the same relation that we used for our observation, and we can compare with our observational results. So basically, the slope and normalization of this input LM relation that after applying the same selection criteria as in our observed sample give an LM relation that match what we observe are the values corrected for the selection biases. So let's have a look at the results. This is what we observe. So this is the LM relation for, in red you can see the high flux values where we excluded from the high flux sample the objects with a temperature below 3 keV, just to have as a comparison the most massive systems. And here the blue points represent the groups analyzed in this sample. So once we apply the selection bias correction, what happens is that this is the relation that we observe for galaxy group, and this is the one that we obtain by correcting by the selection biases. It's steeper, and here you can see the value, is steeper than what we observe, right? So this was expected from the previous plot that I showed from math. But if you have a look to the corrected relation for the galaxy cluster, is actually flatter than what we observe here. And this was puzzling us for a while, but this is simply due by the extra selection that we perform on the high flux sample, the temperature cut. So we tested to applying a different temperature cut, moving from 4 keV down to 0, and actually lowering down the temperature cut, it was causing a steepening, and if you don't apply any temperature cut, the slope corrected for selection bias is actually steeper than what we observe, as we discussed, as we showed before. So it might be possible that there is actually a steepening of the LM relation going towards the low mass regime, and depending which masses we are taking into account, we measure this steeper or flatter relation. This is a very important lesson for eROSITA because first it shows that we really need to take into account the selection biases if we want to use the scaling relation to convert the luminosity into the masses and not be biased on the constraint of the cosmological parameters. And then that it might be possible that a single power law is too simple if we want to convert this luminosity into the masses, and a much more complicated functional must be used. Once you correct for the LM relation, you can apply the same method to correct for the LT relation. You start from, again, from the Tinkermass function, you get the masses and redshift. You assign the luminosity to every single value. This time is the true luminosity because you know the corrected LM relation. You need still to take into account the scatter. You assign the temperature through an input LT relation. And this is, again, the relation we are searching for. You apply the same selection criteria, you fit the data, and you compare with the observational results. And again, what you find is that the corrected relation for galaxy groups is much steeper than the one that we observe in galaxy cluster. Here you can see the number. So indeed, the selection effects are important and need to be taken into account if we want to use the scaling relations to determine to infer the masses that we will use for cosmology. As I said, for some subsamples of the eROSITA objects, we might be able to use other proxies if we can follow up the objects with other X-ray satellites. I don't spend too much time. I want just to say a few words about the MYX relation. The YX parameter is the product of the gas mass and the temperature of the objects. And what is interesting is that basically all the works in literature found very similar slope and normalization for this relation. The slope is always very close to 0.6, which is the value predicted by the self-similar scenario where you have only the gravitational processes. In particular, what is also interesting is that all this work and also the other in literature that I didn't plot here analyzed a different samples that include a different fraction of merging or cool core systems. So it means that this relation is actually quite insensitive to the dynamical state of the object, and this is very, very nice. I will discuss the M-gas and tot relation in the next slide, because you can also use the scaling relations to infer some of the physical processes at work in the ICM by comparing what we observe with the result from a hydrodynamical simulation where you can put some different physical processes. And here, if you have a look to the left panel where we compare the MT relation with the result from Short and collaborators, the dotted line is what they obtained in the simulation when they use or they include only the gravitational effects. And indeed, it's not able to reproduce what we observe. We really need some extra physics. At the moment, we are not able to distinguish with the M-tot relation how important are the other feedbacks. But we can do slightly better if we use the M-gas M-tot relation, because now you can see that, and here we compare the result with the Fabian and collaborators. Now you can see that introducing only cooling star formation and galactic winds is not enough to reproduce the observed relation, in particular in the low mass regime. We really need to include the AGN feedback if we want to match what we observe, in particular in the low mass regime. So indeed, the feedback processes are at work, and they are very important in changing the properties of these systems, in particular the properties of the galaxy groups. A different way to check the effect of the feedback processes is to study the gas fraction in galaxy groups and compare the gas fraction of the most massive systems. Because as we showed at the beginning, for example, AGN feedback can change the value of the enclosed gas fraction, just removing some of the gas from the center. And indeed, also, if you have a cooling star formation, you remove some gases from the intercluster medium that goes into the stars. So we have a master sample covering, spanning over 2 orders of magnitude in masses. So it's an ideal case to study that. And we plotted here the gas fraction for the individual objects versus the total mass. And you don't see very well, but the black points are the individual objects, and the red ones instead are the mean values using different mass bins. The error bars assigned to the red values are the standard errors, which give you a measure of the standard deviation of the mean. The blue line is the best fit of the unbinned data, and is compared with the result of practical collaborators. They studied a different sample of massive objects, and they have also a few galaxy groups there, and they agree pretty well. And you can see that basically the gas fraction in galaxy groups is almost a factor of 2 lower than the one that we have in galaxy clusters. So maybe indeed the feedback processes are changing the properties of these systems. Yesterday, a result from the XXL collaboration appeared on AstroPH. I didn't have time to read and to go through the paper, but this is one of the plots they showed in the paper, and they compare the gas fraction versus the mass with our result. And this was pretty scaring because on one end they found the same behavior, so an increase by a factor of 2 moving from the low mass systems to the high mass systems, but the value of the gas fraction were much lower than what we found in literature. But actually, this is probably due to the fact that for computing the gas fraction, they used the weak length masses that are indeed higher in this paper than the hydrostatic masses that we used in this work to compute the gas fraction. And they actually did a test, and it's in the appendix. What happened if you compute the gas fraction using the hydrostatic masses? And to do that, they used their temperature and our MT relation to compute the total masses and then to estimate the gas fraction. And the result is here, showed with the dotted red line, and is in agreement with what we found. So indeed, we have several papers now showing that there is almost a factor of 2 difference in the gas fraction between these 2 systems. The same thing, or a similar effect of the feedback processes might be seen also when you study, in particular, the radial profile of the metallicity. So here we have the temperature profile for the galaxy groups that I showed, and they are following almost a universal profile peaked around 0.1 R500, similar to what was found for galaxy clusters. This is instead the same thing, but for the metallicity. And although there is a large scatter in the center, there is still a universal decrease with the radius. But the interesting part comes when you compute you compare the radial profile of the metallicity with the one of the galaxy clusters. So although in general the overall metallicity of these systems is pretty similar, and it is around 0.3 solar, when you compare the radial distribution of galaxy cluster, here showed in black, and they have a temperature in this range, with a galaxy group with different temperature beams, you see that when you are in the outer part, so let's say beyond the 0.3, the metallicity at the galaxy group scale is much lower than what we observe for galaxy clusters. And this might still be an effect of the different feedback processes working in the ICM and having a major impact at the galaxy group scale. So this is my last slide. I leave the summary here and I take questions because I'm running out of time. Thanks.
Any questions for Lorenzo? And may I ask, when you show those scaling relations, when you compare your results with the high flux clusters, and I note that there's not only a larger uncertainties on individual measurements on clusters, and there's also larger scatter on the relations.
Yeah, so
that's the opposite of what I would expect.
So there are a few things to say. So first of all, the high flux values that we used here for the comparison comes from the ROSITA data directly. So where they use the one single beta model for describing the surface brightness profile to determine the density profile. And for most of the objects, they have only a few counts to determine the temperature, and they didn't use a temperature profile, but it was an isothermal model applied. Then, for the galaxy groups, our estimation of the temperature and the temperature profile is much better than what you can derive with the galaxy clusters, because you can really measure the iron line to have a better determination of that. For the scatter itself, I agree, it's a bit puzzling. We could expect something bigger than at the galaxy cluster scale, in particular if the AGN processes or other feedback processes are at work. I don't have an answer. For most of the scaling relation, what we observe with this particular sample is that a lower scatter for most of the scaling relation compared with the galaxy clusters. It might be due to the cosmic variance. Other different samples of galaxy groups found indeed a larger scatter. So I think we really need to move to a larger sample of objects to quantify better the intrinsic scatter of the galaxy group regime before trying to give a strong conclusion on that point.
When you do those comparisons, do you exclude the core of those systems?
Yeah, we are excluding the cooling region.
So when you do the scaling relations in the early part of your talk, you wind up leaving out presumably point sources. Do you worry that you won't be able to do that when you have the eROSITA data? And how will you deal with that? Was it an important correction when you got the point sources?
Yeah, indeed. It's playing a bigger role, and we are thinking how to handle that with eROSITA. At the beginning of the mission, we have to indeed, we will be somehow biased about this. We will need probably to strongly ask for X-ray follow-up to take into account that. We can study what is the level of the point sources with the current data, and then apply that correction directly to the flux measured with the eROSITA. But that will anyway introduce some level of scatter that will need to be included as a systematic error in the final results.
In estimating the mass of the galaxies, are you probably accounting for the dark matter, which is probably dominant?
Yeah, we are not determining the masses of the galaxies, but the mass of the galaxy clusters. So we apply the hydrostatic equilibrium equation, is taking into account, of course, the dark matter. It's everything that is including in the sphere, which is within a certain overdensity. And here we use the R500 as a reference overdensity. Yes.
In the gas mass fraction plot, there was the last point was, yeah, what is that last point doing
It's a crazy point. I don't have an answer, but we have a very few points there. So we have a couple of bins. So there might be systematic errors there. So there is in particular this point that is pushing down the gas mass fraction. Yeah.
Are your hydrostatic masses based on the beta model?
This one, yes, a double beta model, yes. So we indeed plan to try to follow your prescription, but we didn't done yet. So we asked for a larger sample of objects, and we are planning to estimate the masses. With
I think we showed that it's critical for high mass clusters, and some show that it's still critical for the groups to do the. I mean, it's more complicated. Double beta model can correctly deal with the central region, but the steepening of the profiles.
Yeah. Indeed, and in particular for some of these galaxy groups, we cannot really measure the properties up to R500, and we have to extrapolate the profiles, and so indeed using a beta model may cause some bias.
Okay, let's thank Lorenzo. He group in October, and he's currently working on advanced electric clusters, and his office is in B234. So if you have any other questions, feel free to ask him. And next is our last speaker this year, is Peter Blanchard. And Peter is a third-year graduate student at Harvard, and he went to UC Berkeley for undergraduate. And he's currently working with Iblc. And today he's going to talk to us about the progenitor of gamma ray bursts.
Okay, thank you. So today I'm going to be talking about the locations of long GRBs within their host galaxies from recent HST observations of Swift gamma ray bursts. So first I'm just going to go into a little bit of background on what we know about GRBs. So gamma ray bursts are characterized by an initial prompt gamma ray emission that is characterized by highly variable and diverse light curves. So we have two types of gamma ray bursts, long and short GRBs. The short GRBs last a few milliseconds up to a few seconds, and the long GRBs last tens of seconds up to hundreds of seconds. Following the prompt emission, we have longer-lived afterglow emission that spans X-ray to visible and radio wavelengths. So we have this sort of physical, picture that has emerged over the last several decades, where we think that this emission is coming from relativistic jets that are launched by accretion onto a central engine, probably a black hole. And we think that the prompt emission is coming from internal shocks in the jet, and then the afterglow emission is coming from an external shock when the jet runs into the medium surrounding the star, surrounding the progenitor. And so to sort of explain where we think this progenitor, this central engine is coming from, there's emerged a couple dominant progenitor models. So for the long GRBs, we have this collapsar model, where we think that the central engine is coming from the collapse of a rapidly rotating massive star. And this model has gained prominence over the last decade mainly from the fact that low redshift GRBs, many of them are associated with supernova. And the short GRBs, we now think are the progenitors are merging neutron star or neutron star black hole binaries. So I'm in this talk going to be focusing on the long GRBs, and in particular, seeing what we can learn about the progenitors by studying their environments. So we're kind of left with no choice but to study their host galaxies. There's really no hope of directly observing the progenitor of a gamma ray burst, as is possible for some low redshift supernova. So we need to go after their host galaxies if we want to infer properties about the progenitors. So as we've accumulated samples of the host galaxies of long GRBs, we've found that they're these irregular, faint, star-forming galaxies. Here's a couple images kind of showing you the types of galaxies we're talking about here. And sort of in addition to this connection with supernova, this fact that we find them in these sort of star-forming blue galaxies also lent support to this idea that long GRBs are connected to massive stars. And we also found that their hosts show low metallicities, which gave support to this theoretical idea that low metallicity is going to be important to maintain the angular momentum required to produce a GRB. But beyond just the global host properties, we can go deeper than that and look at the subgalactic environments of GRBs within their host galaxies. So for a handful of bursts in the low redshift universe, people have done resolved spectroscopy of these host galaxies to study in detail the properties of the environments where GRBs occur. But if we want to understand the population as a whole, we need to resort to other techniques to make use of the full sample of GRBs that we have available. So what we need to do is resort to other techniques like measuring the offset of GRBs from the center of their host galaxies. And also this other technique, just start calling it this fractional flux technique, which I'll go into much more detail later, but for now is just a way of sort of assessing the brightness of the position where the GRB occurred in its galaxy with respect to the total light distribution. And so once we have these samples for GRBs, we can then make comparisons to supernova, because we're certainly interested in how the locations of GRBs compare with supernova. So before we've obtained this large sample of GRBs from the Swift satellite, people use samples of about 20 to 30 GRBs to study their locations in their host galaxies. On the left here, I'm showing sort of the state-of-the-art before this project of the offsets of GRBs from the centers of their host galaxies, shown compared to an exponential disk profile. And this was sort of rough agreement between the two. Also was early sort of support for this link to massive stars. Then on the right here, this blue distribution of this fractional flux statistic, the fact that it's sort of shifted to the right from this uniform distribution, meant that the actual positions of GRBs were highly correlated with very bright regions within their host galaxies. So these two studies were consistent with this link of long GRBs with massive stars. But these early samples were small. They were heterogeneous. They were cobbled together from multiple different satellites. And they were also restricted to relatively low redshifts. And importantly, recently the supernova samples have really increased in size. So the comparison of supernova to long GRB locations has, up until now, really been limited by this small long GRB sample that's been available up until this project. So this was sort of the motivation to carry out this project, where in particular I looked at the last 10 years or so of Hubble observations of Swift GRBs to investigate their locations. So the sample includes about 105 long GRBs observed by Hubble the last decade using mostly WFPC and ACS imaging with optical and near-infrared filters. I drew on about 20 different HST programs using mostly unpublished data. So here's just a redshift distribution of this sample, shown in red, compared to the two samples I just mentioned, showing how we're kind of pushing out to larger redshifts and just the dramatic increase in sample size compared to these early samples. So to actually locate the GRBs within their host galaxies, I use relative astrometry with using ground and space-based afterglow observations to be able to pinpoint precisely where within the host galaxies the GRBs occurred. So once I've done this astrometry for 105 long gamma ray bursts, we can then plot the positions on the HST images, hoping to look for the host galaxies. So the next step here is to identify the host galaxy. So one way you can sort of do this is for various extended objects near the position, you can ask the question, what's the probability that that galaxy was there just by chance coincidence, given the observed sort of number density of background galaxies from galaxy surveys. And for most of the cases, the positions fall pretty much directly on top of a galaxy. So this procedure is pretty straightforward. But there's a few cases where, let's see, there's might not be a galaxy at the exact position where the GRB occurred, and there might be some nearby extended objects that could potentially be the host, or perhaps the host was not detected. So we need to be a little more careful in those situations to to sort of distinguish between those two cases. And in that case, I kind of fold in some the luminosity information that we have to address those cases. So once we've identified the host galaxies, we can then measure the offsets of the positions from the centers of the host galaxies. So here I'm just going to start with showing you the physical offset distribution, so the physical offset in kiloparsecs. So here I'm showing the cumulative distribution of physical offsets for my sample here, shown in red. And so since offsets are non-Gaussian and the uncertainties on the offset can vary considerably, as you saw on the mosaic slide, because I'm sort of drawing on a wide range of various afterglow observations. So for these two reasons, I use a Monte Carlo simulation to get a sense of the uncertainty on this full distribution. And there's also this simulation here shown in this as this gray region here. So this allows me to sort of robustly determine the mean of this distribution and understand its uncertainty. So I think it's interesting to point out sort of the really kind of remarkable agreement between the early sample of offsets here shown in blue, and also that long GRB offsets are considerably smaller than what we find for supernova type 1b Cs shown in cyan here, and type 2 supernova in green. But what we really want to do is make a fair comparison between objects within our sample, because there might be galaxies of different sizes, and to make a fair comparison with the supernova samples, which have different host galaxy sizes. We need to normalize these offsets by the sizes of the host galaxies. So we can really ask the question, sort of where are GRBs occurring with respect to the light of their host galaxies? So this is what I'm showing here, the distribution for host-normalized offsets. So on the left here, there's just a linear scale on the x-axis and then a log x-axis here, making it much easier to see what's going on. So again, I'm showing my distribution for long GRBs in red here. So first I want to draw your attention to a comparison with this magenta line, this magenta curve here, which represents the expected distribution for an exponential disk profile. And you can see that this red line here is shifted considerably to smaller offsets. So long GRBs are much more concentrated than what we expect for an exponential disk. So it really appears that long GRBs prefer the bright central regions of their host galaxies. And in particular, they're more concentrated than the light of their host galaxies. And sort of another way of saying that is that about 50% of GRBs occur within a region of their host containing about a third of the light. So now I want to draw your attention to a comparison with the supernova samples, again shown in cyan and green. And the long GRBs are also more concentrated in this normalized sense than the supernova. And sort of an easier way to kind of look at the differences between these distributions and with respect to the exponential disk profiles by looking at this ratio plot of these distributions. So this is just the ratios of the distributions on the previous slide with respect to the exponential disk profile. So you can see that the long GRBs at almost all offsets, kind of in a cumulative sense, have sort of an overabundance with respect to the exponential disk profile at a given offset. And then it's a much different story for the supernova, which kind of start out with this deficit with respect to the exponential disk. So there are not very many supernovae occurring in the central parts of their galaxy. And then they kind of switch over to an overabundance with respect to the exponential disk. So there also aren't very many supernovae way on the outskirts. So as I mentioned early on, there's this other technique of assessing the locations of long GRBs. So beyond just measuring the offset from the centers of their host galaxies, we want to ask the question, are these positions spatially coincident with where massive stars are forming? So we measure this fractional flux. And so this statistic is just the flux from pixels fainter than the brightness of the burst site divided by the total galaxy flux. So 0 would mean that the burst occurred on the faintest region of its host, and 1 would mean that it occurred on the brightest region of its host. So to do this, we need to extract the galaxy pixels. I do that using source extractor, so we isolate the pixels belonging to the galaxy. And then we need to measure the flux of the burst site. So in most cases, we have sufficiently precise positional determinations that the afterglow uncertainty region kind of just spans about 1 pixel or so, 1 HST pixel or so. So we're pretty good in that situation. But as I mentioned before, we're kind of drawing on a wide variety of different afterglows to make use of sort of everything that we have available. So some cases we have larger error circles and can be quite a bit larger than the PSF of the image. And in this particular case, can be a pretty substantial fraction of the actual size of the galaxy. So a question kind of arises, can we really make a meaningful estimate of the fractional flux in these cases and make a reasonable comparison to the situations we have up there? So to assess this, I just go ahead and measure the fractional flux for the entire sample, and then make this plot here of fractional flux versus this ratio of error circle area to galaxy area. So here I'm normalizing by galaxy area because you can imagine that it's not just the absolute size of the error circle that matters, but also the size relative to the galaxy, because you could have a very small galaxy, in which case it's going to be more difficult to constrain the fractional flux. So you can see that when you go above about 10%, this ratio of about 10%, there's sort of this dramatic drop in fractional flux. And you can kind of think of this as the fact that as the error circle is getting larger, we're kind of averaging over a larger region of the host galaxy and also starting to include background sky pixels. So this is acting to bias the fractional flux to lower values. And you can also kind of see this in this cumulative distribution plot here when I divide the sample up into, divide the sample at this value of 10%. So to make sure we're not biasing our conclusions, we're just going to consider the bursts, the GRBs that have this ratio of less than 10%. And this is what I am showing on this plot here, as well as the distributions for various types of supernova. So again, we've got this red line here for our sample. And it's exhibiting this characteristic shift to the right from this diagonal one-to-one uniform distribution line here, indicating that in this sample, GRBs seem to prefer some of the bright regions of their host galaxies. And I want to point out that when we compare with supernova, particularly the type 1c supernova, there's remarkable agreement with the type 1c supernova, which are related to the types of supernova that have been found to be associated with gamma ray bursts at low redshift. I also want to point out the super-luminous supernova sample in orange here. At this point, we can't statistically distinguish the two distributions to a very high significance. So, maybe there's a hint of a possible connection between the two types of transients. And also, when we look at the sort of ordinary core collapse type 2 supernova, they're consistent with being drawn from this uniform distribution where they don't show a preference for being in faint regions or a preference for being bright regions. But we really want to understand what's driving this observation here, because you can kind of dream up various scenarios in which you might see this. And so we can kind of address this in a way that hasn't been done before by kind of coupling these fractional flux measurements with the offsets. So here I'm showing fractional flux as a function of host-normalized offset, where we see a clear correlation between these two quantities. So the bursts at very small offsets are exclusively at high fractional flux values. And when you go to larger offsets, there's on average you find a lower fractional flux value. While it might not be sort of particularly surprising, given that galaxies are brighter near at the centers, near the center of their host of the galaxies, that you'd expect that if you have a smaller offset, you're going to have a higher fractional flux value. But what's sort of important here is that this correlation, and more importantly, sort of the distribution of points along this correlation, the fact that we find most bursts kind of over here, this sort of explains the fact that we see this shift in the fractional flux distribution to high values. And you can kind of clearly see this in this plot on the right here, where I'm dividing the sample at an offset value of 0.5, and then plotting the two samples in this cumulative plot. So the bursts at offsets, normalized offsets greater than 0.5 follow this uniform distribution, so they don't show any preference for occurring on unusually bright regions. But if we look at the offsets less than 0.5, they're sort of exclusively at high values of fractional flux. So the full shift that we see in the total distribution of fractional flux is really being driven by these bursts at small offset. What this is saying is that it's not just the presence of a bright star-forming region that affects long GRB production, which is sort of the interpretation that people had following those initial studies of fractional flux. But it's really the fact that we mostly see GRBs coming from the central parts of their galaxies. And so this is saying that the star formation in the central regions is the more favorable for long GRB progenitor production. And it's an interesting question of what about the central regions of their host galaxies is driving this. So sort of from a theoretical standpoint, beyond just a single star scenario, it's perfectly viable to have binary interactions that could lead to long GRBs. And sort of on the observational side, we've seen that there's high fractions of massive stars live in binary systems. So maybe in the central parts of their galaxies, there's sort of an enhanced binary interactions that could be driving this observation. Also, maybe there's differences in the initial mass function as a function of radius in the galaxy. So maybe more massive stars are forming in the central parts of their galaxies. So I think it's a really interesting observation, and I think progress really figuring out what environmental factors are driving this is going to come from really detailed studies of massive stars in the local universe, kind of studying the long GRB progenitor analogs that we can see in detail nearby. So just as a quick advertisement of work in progress, so kind of turning it around and instead of trying to learn about GRBs and their progenitors, using GRBs as probes of their galaxies. So kind of in analogy to quasar damped Lyman alpha studies where people can measure metallicities and hydrogen column densities of the CGM of galaxies at high redshift. We can try and do this with GRBs and be able to probe kind of a different regime of impact parameter that is really sort of not being probed by quasars. So we have this nice large sample of offsets. We can then go see which ones we can measure metallicities for from their afterglow spectroscopy. So you go out, get a spectrum of the afterglow, you can measure, if it's at a high enough redshift, you could measure Lyman alpha and metal absorption lines for that particular line of sight. And so if you then combine them all and just plot them on the same plot, we're sort of probing kind of in an average sense what may be going on in long GRB host galaxies. So this top plot here is metallicity as a function of offset, and then hydrogen column density as a function of offset. So I really think it's kind of an interesting way to study high redshift galaxies using gamma ray bursts probes. And it's kind of interesting what's might be going on here. There's sort of this large range of hydrogen column densities that we see in GRBs. So maybe these ones here are GRBs that are kind of ionizing their local environments or something like that. So just to end on a summary, I looked at the last 10 years of HST observations of Swift GRBs. I found that GRBs are more centrally concentrated than what we found before, and in particular more concentrated than an exponential disk profile. So it's really looking like the star formation within about a half-light radius is sort of the most favorable region for long GRB production, and that other environmental factors beyond just metallicity, which has sort of historically been the dominant, what people think is sort of the dominant environmental factor driving GRB production, but maybe there's increased massive binary fractions at the central regions of GRB hosts. So I think it'll be interesting going forward to really pin down what's going on in the central regions of GRB hosts. Thank you.
Any questions for Peter?
So earlier in your talk, you showed that the distribution of LGRBs is more concentrated to central brightly shifted galaxies compared to supernovae. Now I was wondering, is that a correct statement?
Yes.
So I was wondering how much of that could be influenced by observational effects in the sense that the supernovae are typically discovered in optical where the galaxy is bright, so maybe miss the ones that are in the central region where the GRBs are discovered in gamma rays where the galaxy is pretty wide.
Yeah, I think there's definitely probably observational effects that are going to come into play here, and maybe we're not finding. There are supernovae that are going on in the central regions that we're just not seeing because it's harder to see.
Are there redshift sample comparables between the supernova sample and the GRB sample? Because, for example, if the star formation history is more nuclear at higher redshift or has a different spatial distribution, you might not be able to compare them one-to-one because you're just looking at different redshifts.
Yeah, that's an excellent point. I'm kind of using many different comparison samples. Some of them are comparable, like the core collapse samples are from the GOODS survey, so those are kind of closer in redshift to what the GRBs are. But that's a good point. The some of the samples are low redshift supernova samples, so there could be comparison issues there.
Are all the supernovae that accompany gamma ray bursts always type 1b?
So they are always type 1c broadline supernova. So they show, very broad.
It's always one type of supernova.
It's always one. Yeah, it's always one type of supernova. Yeah, and so I think it'll be interesting when we discover more of these 1C broadline supernova to study their locations, because right now we have pretty small samples of those to compare to, which is why I was mostly comparing to the 1Cs.
Any other questions for Peter? Finally, I would like to take this opportunity to thank everyone to attend our Higher Nature seminar this year, and have a safe and happy holiday. See you in the new year.
Can you use any other telescopes besides Hubble? Can you do any ground-based telescopes?
So the